and we'll get going. And look, welcome to week 4, and look, we are 1 week away from the assessment task number 1, which is due in week 5, obviously, on the Thursday night at 11:45. So hopefully people are on track with that, and making a little bit of progress there, so that we can actually get it done, I suppose, and get it out of the way before other subjects become available and due. So this week is a quick overview of the physical sciences strand. Now, it's not meant to be a detailed view, but what we'll do is we will go into a little bit of the science, and we'll talk a little bit about how this week has been set up and what it's meant to achieve. We've got our first assessment task next week. So clearly, we haven't done physical and chemical sciences. We only had a 1 week overview of each. So for that reason, we've opened up the assessment to allow you to look at other strands, to other sub-strands of the ACS, and not just be stuck with concentrating on ones that obviously are quite new to you. So this week we begin by talking about the ACS as a continuum, and the reason why I put up the initial video at the start of the week is to really for the early childhood folk, because you're silent really in the ACS. Let's face it, we've got foundations to 3. The reality is the foundation to 3 years are very much concerned with the continuum. So it's a continuum of understanding. So you may have some very, very bright kids at year 1, and you may be using some of the year 3 curricula. So it's not age specific. It's really about stage learning rather than age learning at that first F to 3 level. So the physical sciences, for those of you not familiar with it, it's the one that talks about nature of forces in motion, matter and energy. So it's really emerges into the adult and secondary fields of physics. So the 2 key concepts developed in the substrand, that forces can affect the behaviour of objects and energy can be transferred and transformed from one form to another. So I'm really trying to simplify this here, because a lot of people get put off by the physical and chemical sciences. We consider them hard, and our aim is to actually break that down. And that's why we work through Russell Tytler's notion of representations. We try to look at learner representations, and we take what are complex representations and we try to break them down into things that are quite simple. And which brings me to Loxley. So your chapter for Loxley, chapter 7, if you haven't read it yet, do. And the reason I'll come to this again later in the session, I'm getting a lot of questions from students about the misconception task. And some people are actually just basically coming up with a misconception themselves, tripping up the students through teacher-led questioning, and then basically saying, I have evidence of a misconception. Well, that's not the task. Okay, you may have a misconception there, but chances are you've kind of led them into it. So a misconception is really teaching from a very, very open constructivist position. Okay, so the aim is to get the learners to manifest the information, and from that information to then use your questioning skills to have a look at the levels of understanding that are implicit through it. So we're going to go on this. So our 2 focus here really, we'll just go back now, forces and energy. And they seem quite amorphous concepts, but actually they're really, really quite simple to teach and a lot of fun to teach too. Through the substrand, you get an understanding of an object's motion. So we talk about things like direction, speed, acceleration, and how that's influenced by a range of contact and non-contact forces, such as friction, magnetism, gravity, electrostatic forces. Now, they may not mean much to you at the moment. Okay, someone's got a note there about volume. All right, let me just check. Oh, hang on, I'll go back. Right. Let's have a look. And I'll just get in now and look at the volume controls and see what's going on. Computer audio, so let's have a look and see if there's a problem there. Is that any better?
Colin, this is Maxine. I just came in. I can't hear you very well.
Right, okay. Let me just check what's going on. All right. All right, is that any better now? Can anyone hear a little bit better?
Not really. I can't. It's quite soft, your voice.
Is it really?
It's normally much louder. I mean, the mic.
All right, is that any better?
Yes, that's better. I can hear you now.
Okay, lovely. All right, thank you very much for letting me know that. I have no way of knowing that apart from being told, so thank you. Let's get going, and we'll resort back to where we left off. So we're talking here about some of the science. Now, what we're going to talk about tonight is give you some frameworks for looking at this. Now, we've split the science up into 2 different weeks. So this week we're going to look at electricity and energy, and next week we're actually in week 8 and 9, when you come to the tasks in week 8 and 9, you look at magnetism and a related concept there. So we're actually splitting it up because the body of knowledge is too great to cover in just a short period of time. So we're going to be in some way strategically negligent, but we are going to hopefully give you enough information to be able to go ahead and teach these subjects confidently. So we're going to look at the understanding of energy when we talk about energy and how energy transfer is associated with phenomena including motion, heat, sound, light, and electricity. So even though these are huge concepts, they can be narrowed down. They can be narrowed down and taught effectively. So we can appreciate the concepts of force, motion, matter, and energy, and how they apply to systems ranging in scale from miniature atoms to the universe itself, to something so big that we can't imagine it. So it's a huge field. It's a huge expectation that, you know, this can be dealt with by teachers in a classroom, but it's quite a real thing to do, because if we take the science back to the learner, to what's going on in the learner's world, everything can be developed from that point. And that's what we're going to assume today. So Professor Mark Wetherell, I've put a little video up from him there, and this is again for the early childhood folk. When we look at the ACS, you know, the early childhood folk and the preschool teachers often feel left out, like they've got to, you know, try and translate the early years framework into the ACS and then try and deliver and teach something. You don't need to do that. Just think stage-based learning. And Wetherell talks about teaching to and teaching from. So in the early years, teachers are teaching to the transition into school. And sometimes, you know, when you're teaching the upper years and higher years, you know, you're teaching from a perspective. So you can scaffold and backward chain things, you know, so that it becomes learner appropriate and relevant. Now, Mark Wetherell explains this really well. And, you know, he talks about catering for multi-age and multi-abilities. He talks about content being age as well as stage appropriate. And therefore, the ACS was never intended to teach year one, you know, curriculum, year two curriculum. It's actually stage-based. You can dip and move around that curriculum as much as you like. And again, the qualification being there that you as a teacher have made a professional judgment about the appropriateness of doing that. So have a listen to Mark Wetherell. It's a short video, but he does explain the concepts very well, and I think gives some relief to the early years teachers. The outcomes this week. We're looking at locating, describing, identifying, the same words we always use. And again, we're relying very much on the Australian curriculum, the physical sciences, how we can explore them in the classroom, and of course we're trying to lead to some common misconceptions from the chemical and physical sciences. And again, I point you to chapter 7 in Loxley. You know, it's an actual critical chapter. When you look at it, it's talking about teaching for assessment, and it looks at formative assessment, it looks at diagnostic assessment, and each of the stages of the inquiry process, how you teach for it. And look at the section in particular on diagnostics. I think it's around about page 84, you know, because I'm getting the same question from a lot of people, you know, which indicates that when we teach this misconception, we've actually got to create understanding from the learner's perspective. So when we look at terms this week, physical science, misconceptions, and a new one here, misconception of a misconception. So make sure when you're looking at a science misconception that, you know, you've got it located at the right stage of the ACS, because if you're teaching a misconception or you're exploring a misconception and it's not age or stage relevant, then chances are you've got to question how effective that teaching may be, whether you're actually on the right track. So just make sure that your misconception can be mapped onto the curricula that you intend to teach. So when we talk about content mapping, there's a couple of things we need to know in the physical sciences. And again, we don't need to, you know, to become fluent sort of physical scientists in our own right, but we do need to build our scientific literacy around science. And that's really what, all the exercises in Loxley this week, and I deliberately kept the reading quite short. So when you look at Loxley, the exercises in Loxley are all geared towards building your scientific literacy. We look at energy, and we know that energy, we talk about conserving energy. We've got different types of energy, okay? And we've got kinetic energy is moving energy, and we've got battery or stored energy. And so we've got all these different kinds of concepts that come through, and they're quite well explained. But we can strip that entire section on energy to make it teachable down to these couple of points. Okay, we can see it. And the whole notion, one big misconception, of course, is, we see the blue moon exercise in Loxley, the reading where the child says that all the water is going to fall off the bottom and the sides of the earth. Of course, gravity, the concepts of gravity are not well understood. And gravity fits into quite a few of the physical science elaborations. We look at forces. We've got Newton's 3 basic laws. Okay, object continues unless acted upon by an external unbalanced force. So we've got things like resistance, and we've got things like friction, and of course gravity too is one of those forces. F equals m by a. Okay, force equals mass by acceleration. So the heavier something is, the mass, the more force we are going to need to move it. Really simple principles, really, when you look at it. I don't know why we get scared about these things, but we do. For every action, there is an equal and opposite reaction. And, some of the best exercises we see online, and we'll look at in weeks 8 and 9, balloon rockets and soda rockets or soda racing cars, great things that you can actually explore. So what we're doing here is just trying to strip down what we think is really vague and really, shapeless sort of scientific knowledge to something that we can teach. And if we look at energy, we can strip it down to 4 simple points. If we look at forces, we can strip it down to really Newton's 3 laws. If we're building curricula around that, then we are doing some good science in our classroom. Same with light. Okay. Now, light is a really interesting one. We can look at the electromagnetic spectrum, and we can see in here that the light, there it is there, right in the middle, and how, depending on where you are on the spectrum and what form the light is in, it's going to process and appear differently. We can look at the functions of light. Okay, we can talk about absorption. White light equals ROY GBV, and if you don't know what they are, find out, but it's red, orange, yellow, green, blue and violet, and they are, of course, the colours on the spectrum. And an object appears green when there's an imbalance, because green light is being reflected and the other colours are being absorbed by the object. We've got our theory of light. Now that's not, that's a little complex, but that's not off the planet. Okay, we've got 6 possible options that, when combined, make white light. But, however, when something is reflected, we start to bring in the colour, the notion of colour. Refraction. Light bends. It slows down in thicker medium glass or water. Why does it do that? Kids have fun explaining that one. Reflection. It bounces back. Light can hit a surface, okay, and the angle of incidence is the angle of reflection. This little angle down here. That's how we see things. So light too, we can reduce to 4 simple principles. Okay, we can actually take these really complex science ideas back to a stage where we can talk about them. And that's what we've got to do if we're going to be effective in our diagnostic stages and that engaged stage. We need to build our science literacy as teachers to the extent where we can help kids identify and articulate their understandings. Sound. Sound travels in waves, and again, we can reduce it to 4 simple principles. It's slower than light. It's fastest through a solid, then liquid, then gas. And there's no sound in a vacuum. So that puts an end to, the explosions in Star Wars in outer space. It kind of, if we can get these concepts across, we can actually do some really, really good fun science. Electricity. Again, let's strip it down to 4 basic concepts. Continuous path for electrons to flow creates electricity. Energy, to push the electrons. So voltage is measured in volts, current is measured in amperes, and resistance is measured in ohms. It slows current down. So we have this continuous flow, and we can manipulate a circuit to manipulate that flow. So that makes us very powerful. That makes us really interesting as people and as scientists. So in here, just by building our literacy, 4 simple concepts for each of the physical sciences, we can become conversant. We can work from a position where we can help. We can become the more capable other in a conversation about scientific concepts with our students. A couple of resources this week. Professor Dennis Goodrum, as usual, from the Australian Academy of Science and also the founder of the Australian Curriculum of Science, Science Curriculum, says that good science informs our decisions. The health, the food we eat, the environment. So you can see very much that Professor Goodrum here is talking about bringing the science back to the child's level. And it also then enables us to answer interesting questions. And I really want to put those two facts up, because what we've got here is understandings, science understandings, and science inquiry processes. Now, when you're teaching or looking at your misconception, okay, you are going to explore that misconception, not by holding something up in front of your class and saying, this is what it is, this is the answer to that question. You are going to do it by posing an inquiry process and guiding the children slowly through formative assessment, teaching formatively so you can drive them towards deeper understanding. So when you look at this task, I'm getting a lot of students focusing on the understanding, the science understanding of the misconception. In other words, the science. I'm going to beat the children around the head with the science. Think about your approach. The task here, in the misconception task, is actually asking you to set up an inquiry process, to set up a pedagogy that is going to enable you to answer those interesting questions. Because let's face it, you're not empowering the learners if you send them away with a fact about an acorn. There's an acorn living inside this little nut, there's a tree. It's not going to empower them. But if you ask them what they think is in there, and you talk to them about their concepts, and you build that from the ground up, then you are going to get a lot more movement in your classroom. So when we look at this, we've got some interesting questions. We've got answers made up from the ACS understandings, skills, and human endeavour. Please don't focus just on understandings in this assessment task, because when you put your learning sequence together, you'll actually be identifying how you're building inquiry skills to change and shape these understandings. That's really what this task is. A little resource here that I've put up here for you. Anyone been on EdTV or EdTED? Fabulous resource, emulsion, and believe it or not, the complex process of emulsion and heat transfer is done beautifully through a little video on baking cookies. Now, again, is that notion of pulling back science, pulling it back away from the complexity of the laboratory and putting it in the hands of the kids. How can we find tasks? How can we find challenges? How can we find concepts that kids can work with and then generalize into science understandings? So let's not start with the problem. Let's not start with the misconception. Let's start with the experience. And from the experience, let's see what they understood. And once we work out what they've understood, we can then start to move it towards a scientific dimension or a scientific understanding. So if anyone hasn't been on TED Ed yet, please go and have a look at it. Some really, really good resources. And the reason why I throw resources up there is I know some of you are remote, and I know some of you don't have access to laboratories and to scientific resources. So we're going to talk a lot about simulation. We're going to talk a lot about other exercises and resources that's going to enable you to explore concepts with learners in a flipped scenario, okay, or a flipped classroom. Resources, everyday physics. That's what we're talking about, everyday physics. And we can look at, for instance, static electricity, force and motion, magnetic forces, Newton's third law, action and reaction, his second law, why we fly. Okay, that's how we fly. Newton's second law. Mobile phone, we can use a mobile phone for radio waves, music, satellite. And a microwave oven, we can use that to explore electromagnetic waves. So, we have these resources on hand. We have these resources on hand. We do not need to be complex in our scientific settings. We do not need to be technical. We do not need to be clinical. We can actually have a look at some very, very common aspects of the student's life and experience, and we can bring science understandings to those. Another resource that I'd really encourage you to look at, Google PhET, P-H-E-T, and you will find, I think there's 3,000 science simulations on the PhET site, and we look at some of them. For instance, I point you to John's Revoltage this week, all about static electricity. Great little exercise where kids can actually monitor, they can move his leg and his arm and up to the point where John gets a shock. There's a whole range of activities in there. Another one that I've put up for you this week, of course, is the skate park energy skate park simulation. So we'll talk a little bit more about that as we go on. But, you know, they're there for you to look at and they're there for you to explore. But we're not going to concentrate too much on science content at this stage of the course, because we're really looking at the teaching of science. We're looking at the pedagogy, we're looking at the misconception, and we're looking at the inquiry process. That's really the focus of your first assessment task. So when we look at mapping misconceptions, you know, where are they coming from? You know, let's not have any misconception about our misconception. If you say you're teaching a foundation year, then, you know, let's hope that your misconception can be identified in the curricula of that particular foundation year. So the moon only appears at night. Yes, we can see that. Earth and space science at a couple of different levels. All metals are magnetic. We can see it in the chemical and physics. Diamonds are indestructible. Okay, a myth. Often appears. I was watching a movie the other night where that was the case. Again, we can see it appearing in the curriculum areas. Boats are made of materials that float. Okay, again, another common misconception. And we can see them appearing. No mammals lay eggs. Okay, we can see that in the biological sciences. Penguins only live in the snow. Again, biological. Sharks eat people. Biological. Okay, is it a misunderstanding? Is it a misconception? Okay, it's certainly a phenomena. I think, you know, they're now putting it down to the similarities between people and some of the sharks' normal food sources. So in actual fact, it's a species-oriented problem. Misconception. Humans lived at the same time as dinosaurs. It's a beauty, isn't it? But it does come across in the biological sciences, and it can be examined and explored. All birds fly. These are little misconceptions. And these misconceptions are, you know, we know they exist, but it's the skill in bringing these misconceptions out. It's the teacher, the pedagogy, bringing out these misconceptions. That's the skill. Therein lies this assessment task. Summer occurs when Earth is closest to the sun. Melting is a chemical change. It's an interesting one. Look, it appears a couple of different year levels. Plants always grow upwards. Very interesting one. Sound travels best in the air. Interesting. Yellow is a primary colour of light. And living things are either plants or animals. So we can see, you know, a range of misconceptions. All I'm doing here is not saying these are the ones you should be doing. I'm saying, look, you know, if you're doing a misconception, make sure you've got your substrand located, make sure you've got your age and stage levels right, okay, and make sure that what you're suggesting, therefore, as a learning sequence or a teaching sequence is appropriate. So in other words, interrogate your idea. You know, take a cricket bat and hit your learning sequence with it, take it out on the patio, hit it with a cricket bat, and just make sure it stands the test. You know, am I really teaching the right misconception here to the right group of people? Point number 5, I'm just going through some resources, the flipped classroom. And this one is on sleighs and forces. And again, a really great little interactive. And you can notice it's got a little quiz button here, which is really good. So we don't need, you know, to have a whole lot of resources in our classroom. It can be difficult. But using this little simulation, we can set up a really simple POE, a little inquiry task. And this device actually allows us, you know, to make predictions. What's going to happen if I increase the level of force, you know, and I change the surface from carpet to wood or to something else? What do I predict is going to happen to the car? What will it do? So we can make predictions. We can change the surfaces. We can, you know, change variables. We can add ramps and obstacles, okay, to see what happens. We can increase the force. Up here you can't see it, but there's a little red and yellow button and the lever comes back and you can increase the force to high, low, or somewhere in between. We can explore the concept of friction, and we can even do some diagnostics with the quiz function. So when we're testing misconceptions, we don't need always, you know, to have a pen and paper thing. We don't always need to finish up with the table. And I had some really good questions this week on the forum about what counts as data in this task. You know, what are we actually analysing? I'll talk more about that later. But we're only limited by our imagination. If we flip the classroom, there are some great simulations around that we can actually use. Another one, circuits without tears. I mean, it's a great little one. I apologise for this. It's a really badly shaped circuit. I threw this together quite heavily, quickly. My main aim was basically just to demonstrate how powerful PhET is, how good its resources are. But you don't even need circuit boards. We don't need that equipment anymore. We can do it all. I mean, it's lovely to cut the wires and use wire shredders, and it's fantastic to do that. Great experience, hands-on for the kids, particularly some of the boys in your class. But when we look at this, circuits without tears, it's got inbuilt investigations in it. So we can set up a sample. We can look at the complexity of the circuit we're building. It can be a simple circuit. It can be a parallel. It can be a series circuit. Depending on, you can get them to design and test different concepts. They can build the circuit from scratch. Okay, I do apologise for mine, but you can see there's a battery in there. You can see there's some resistors. You can see there's a light globe. And it's a very easy thing to work. You can bring breakers, resistors. You can test for conductivity. Here you've got a couple of different, you've got a little menu in here where you can actually open up the menu and you can test different things. You can put a paper clip in there to see where that works. There's a pencil. There's a whole range of different tasks. And we can increase the circuit complexity, okay, moving from series to parallels, etc. And we can also use ICTs. So we can get the kids to actually make a video of their solution on the screen, working and functioning. And then they can come to class the next day or sit down with their peers, do a small presentation, replay their video, and explain scientifically what's happening. So we don't need actual class resources. It's all about the teaching. That's what we need to take care of. That's what we need to function on and focus on. One of the tasks I asked you to do this week, and I noticed 2 students have already done that already, which is fantastic. I'll come to their resolution at the moment, is come up with a concept map. Because really when we're talking about science literacy, and we all as teachers, we roll them out, don't we? How many assignments have you done at CQU where you've talked about concept mapping, where you've gotten students to, post their process and try it, apply it to yourself, let's test the more capable other. Now, there's no shame in not knowing physical sciences, none whatsoever. But there is a shame in not learning it. I think we're all becoming teachers because we value education. So when we look at our concept map, the task was do a concept map involving electricity and magnetism. And of course, electromagnetism, they are related concepts, these 2 ideas. They come together. But do you know how and why they come together? So we can look at electromagnetism. It's a force. It exerts a push or a pull depending on polarities. Electricity can be one of 2 things, static or current. That's as complex as electricity gets, static or current. If it's current, it's contained in a circuit. Okay, and then we know, for instance, current electricity's got some other principles. We can go through and map our understandings. Please do this. And, don't be frightened to throw it out there into public. I mean, I've seen 2 students do it already. Really courageous. Great that you do it, taking a risk. But you're going to be in front of a class taking a risk teaching this stuff. How good is your concept map? How good is your literacy? Will it stand up to interrogation? And there's some really simple principles. You just map your understandings and they just keep rolling out. They can be natural or man-made. They produce a field. The Earth is a giant magnet. Earth's magnetic field is caused by circulating electric fields that surround the molten core. Okay, it's really just a big circuit. A compass is an instrument that uses a freely moving magnetic needle to indicate direction. And electromagnetic is a piece of iron that becomes temporary magnet when electricity flows through. So these are not deep understandings I've charted here, and there's no formulas here. Okay, there's no great Earth secrets. These are really simple principles that you could dialogue with students about. Look at your understanding of electricity. Static is pretty well covered there. Okay, current electricity, we can then start to break it down into the different types of circuits. And what is a simple circuit? What is a parallel circuit? How do they function? How do we know the difference? What happens if there's an energy block in a parallel circuit? Will we still have light? A series circuit is a simple circuit. We can then talk about switches and we can then talk about the use of electricity around the home. It's a concept map. Okay, notice the deliberate absence of science and scientific formulae in this concept map, because when you need that, you can find it. But chances are, to get your teaching off the ground, you're not even going to need that knowledge. All you're going to need to do is have a literacy component around your own practice, around your own understandings. So if you haven't done this task, you owe it to yourself to do it. It's a really important task. We repeat it again later in the course when we look at the chemical sciences. But, please do think about building your literacy and what steps are involved for you. I know when I teach science, I always do a concept map beforehand just to refresh myself about the concepts involved in teaching this subject, the likely directions it could go if I lose control of it, and some of the obvious misconceptions that are going to pop up that I really ought to have some researched answers to. Okay? Or be courageous enough to say, look, that's a really good question. I'm going to go away and find that out for you. Or better still, why don't you find it out? And so look at your concept map. If that's too difficult, break it down. Do one on magnetism and then do one on electricity. So you may be thinking, wait a minute, magnetism, electricity, electromagnetism, oh God, that's out of my ballpark. Do one on each. Either way, you are going to come together with really rich understandings. And magnets, we can talk about dual polarity. We can look at the initial things, and magnets have forces, and they have a north and south. And from there, we can actually unpack a lot of knowledge about magnets that we didn't think we had. So we're not going to be thrown when a student talks to us about it. And the other thing I want to point to is, look at these things, arrows. Now, science is rich. The literacy of science is rich in symbolism and in context cues. A periodic table, for God's sake, look at that. A huge concept. Symbolic, okay? Not real. Everything's reduced to symbols. The relationships here are reduced to symbols. The arrow is a powerful literacy tool. And when you get them to sit down and draw a science concept, then get them to put in the arrows. Ask them what's happening. Get them to draw a cartoon. Okay, it goes from this to this. What's happening? Put in some arrows. Give us some symbols. And of course, we can look at electromagnetism there, the common link. Okay, and there was a little animation that was supposed to play there, which is not good. Oh, there it is. And electromagnetic. So that they are related fields. And we can look at electricity, again, static, current, moving electrons. There's really not too much that we need to learn about this. We can learn it. We can teach it. What's more, we can have a lot of fun with it because there are some great resources out there. Here's one from Renee and Caitlin. Now, these students have actually put theirs up on the student forum, which is fantastic. And what I love about this, it's just, concept maps just so personal, aren't they? I mean, look at these wonderful diagrams. That's one of the best little atom diagrams I've ever seen. And here we've got, I think this is Renee. And Renee's got all her own little symbols thrown in here. Now, the challenge with using our symbols is we've got to develop a literacy for those with our learners. If we're throwing in our diagrams, it's lovely on conductor and electromagnetism. Understanding's really clear and apparent. Now, Renee would be ready to teach this subject. Okay, she's grounded in the basics here, is ready to go out there. She's got her framework together. She's identified the key relationships. She knows where she wants to take the key concepts. Now look at the conductors up here. Everything's in there. Attraction, repulsion, a little diagram here. You can see it, which also represents a model of the Earth. That's how the Earth also developed its own magnetism. And we can see electrons moving from one place to another. Really elaborate and rich understanding. Quite a productive understanding. Please have a go at this stuff. Post it and then talk about them. Talk about them. Talk about people's interpretations, because here is the skill in assessment task number 1. Looking at someone's representation and actually being able to say, well, what would I ask about that? Okay, where do I think that's going? What are the strengths with it? How are the relationships justified, explained? These sorts of questions, make the good questions. So you'll see Renee and Caitlin have both put theirs online, but talk to them about it. If you don't have time to do it, at least, talk to students who have and interrogate, question, ask, practice your questioning, if not your content knowledge. So let's get to the forums this week. And I'll pause there and ask for any questions straight up. Does anybody have a question that they would like to raise?
Hi, Colin, it's Kelly.
Kelly, yes, fire away.
Sorry, I just missed what you said at the very beginning of the recording. There's 2 due dates. One says Friday at 11:45 and another one says Thursday at 11:45. Could you just confirm which is the due date?
The due date is the Thursday at 11:45, yeah, and that's the one that should be on the subject prospectus online.
Yeah, no worries. Thank you.
Yeah, no problems. Yeah, I have had that question before, so hopefully it's if everyone's on board with that. We'll see what happens. Hopefully people are on board with it. I'll actually send out a message just to that effect so people can be clear. So I had a couple of really good questions this week, and Loretta, as usual, always comes up with a good question. And when we get into the discussion board in the Q&A, now I just want to point out too that Renee and Caitlin both posted their concept maps in the general discussion forum. If you go down, I'll just go back to the homepage here, and you'll see in week 4, I've actually got a forum there, getting ACS familiar task. So it's that's the task that we've got you to do with the concept map, and that's the forum where you post it in. So if you go there, you'll see that we can actually, there is the forum, the discussion board, and there is Renee's and Caitlin's 2 responses. Do have a look. I'm really delighted that they're up to date and thinking in the way they're thinking. Some really good science developing there. So when we get to the Q&A, we can actually have a look at some of the questions that come up this week, and I'll drag it up and put it down. But what I really want to do is, while I'm adding lib here, I really want to hear from you guys if you've got any questions. So when we look at this, Loretta asked a really good question about what counts as data. So when she's analysing the student responses, how far does she go with that analysis? Students of different age, for instance, which I think was Loretta's question. Does she simply analyse one set of those students at the age that she wants to teach her learning sequence to? Or does she look at all of the differences around a misconception, when it's most vulnerable, when it first appears amongst the age of the learners? And look, I think that's what counts as data in this case. If you've got a mixed age group, then definitely count all the data. And it brings me to a question to what Maxine said, what do I report? A very good question. Have a look at this online. And what you're doing is content analysis. If your students have given you a written response, then you're doing a thing called CA, or conversational analysis. It's got a rich history going all the way back to the 20s. Clive Gertz, great researcher. Harvey Sachs, a great researcher in the 70s. These guys all applied conversational analysis. And what they do is they look at, conversations are basically turn-taking. You say something, I say something. And with teachers and learners, of course, there's a power relationship there. So the aim, of course, is to work within that and try to manifest it and make it a learning relationship, not a power one. But when we talk about conversational analysis, it's the turn-taking going on. And the aim of conversation analysis is to record the conversation and then get to the bottom of the themes and understandings of that conversation. So when Maxine analyses her text, she's going to be looking at the key words that students use. And those words are going to come together or converge around certain common understandings, and they're going to diverge around certain other understandings. So when Maxine reports this, she'd look at the areas where students converge, where they're similar in their understandings. Then she'd look at areas where they're perhaps different. And then she'd compare those to the scientific understanding. So what you report is the data you get. Okay, if you've got students talking about, this is my conception, and this is why, and this is where the moon goes, how many are doing that? Who are they? Okay. Then when you've got that, where do they converge? Where do kids say different things? Once you've mapped that, you can then look at the science of it and see where the science sits. Does it sit outside all of their understandings? Is it common to some of their understandings? Do they have parts of the science but not other parts? And the only way you can make those decisions through analysis is to actually sit down and do that analysis, to actually look at where these understandings come together, where they drift apart, and where the science sits. Once you've got that, you'll quite now know what you're going to report, and you know what misconceptions you're going to be working with. Rachel had some very good questions early in the week and was firing them out rapid fire. The criteria for reporting to parents and or carers. Now, if you look at the assessment task number 1, there is a criterion there for reporting. And of course, reporting is kind of a ridiculous word in many ways, because it's got common misconceptions and misunderstandings. When we think reporting, we generally think, submitting grades and the high stakes stuff. But in this context, reporting really can be that, if you want to do it that way. But primarily it's really about conversing or conferencing. How are you going to conference with parents, carers and learners? What's the outcome of this? what sort of assessment reporting process, about learning are you going to develop and include? And when we talked about this initially, we suggested rubrics were a good way to do it. There's also portfolio, there's also interviews, there's rubrics and interviews, there's peer assessment. There's a range of ways for doing this. Work out where it fits and what sort of skills you're trying to teach in this learning sequence, and that will be the most appropriate way to think about reporting. Any questions about the concept so far? Or any other concepts from you? I'll just check and see whether the chat is there.
Hi, Colin. It's Kelly again.
Kelly, fire away.
Just when you were talking about reporting, my misconception is a very general one, but what I've come to when I've done my teaching sequence, what I'm looking at is getting all the pieces of that and putting it into some sort of like a newsletter or that can go out to the parents of what we've learned about. Would that be appropriate as a way of reporting?
Kelly, that's beautiful.
Oh,
yeah, it's innovative and it's owned by the students and it's fantastic. Yeah, great idea. Beautiful conference.
Thank you.
Yeah. And Rachel also came up with another question. Asked about what sort of lesson plan we're looking for your learning sequence to be embedded in. Well, we're not talking about a lesson plan, we're talking about a learning sequence. So you would go from a learning sequence to a lesson plan. So please don't think that you're needing to produce a lesson plan here. What you've got is a learning sequence, and that learning sequence will be rich in pedagogy. That pedagogy may be the 5 E's, it may be POE, it may be the 4 C's, it can be a range of different inquiry processes, but it must have 3 clear stages: the diagnostic, the formative, and of course the closing or the summative. So once you've got those 3 aspects and you've got a learning sequence, the key thing to do in this assessment task is demonstrate how each of those sequences unpacks the misconception or focuses on the misconception. So for instance, in the engage stage, it'll be questioning. And, Loxley on page 85, I think it is, maybe more. No, sorry, there it is, page 87, gives you 3 really good examples about what to do to tease out understandings at the, at the diagnostic stage. So there's some things there and why you would do it. So you may pick one of his 3 suggestions. He then goes on to look at the redescribing stage, as he calls it. And again, he offers, 5 different suggestions about what you can do as a teacher at that redescribing stage. So when you're looking at how do I present this? Present a learning sequence. The learning sequence must address that initial engage stage, okay, the diagnostic stage. It must address the redescribe, and it must address the application phase. So, and that's not necessarily going to be in a lesson plan, okay? The format is up to you, but it must be explicitly connected to your misconception. What you're trying to do is tease out these misconceptions. Paula had a really interesting question. And again, it's about where the misconception comes from. Now, in this task, we are asking you to be constructivist. Okay, you are working here to break down, first of all, to identify, really. You are deconstructing misconceptions. You are then reconstructing them through your inquiry process, and then you're co-constructing them, by setting up applications, an application phase where the learners are starting to consolidate and manage their knowledge. And for this reason, who owns the misconception? It's got to come from the students. You can't simply say, here is an acorn, and inside this acorn is a tree. Who can tell me? You can't do this sort of thing because it's really the teacher's got the answer, and this is the message the kids get. And science is just really something someone else knows about, not me. So the key here is to have a notion of working constructively. Okay, who owns the misconception? Work with what comes from the data. Once you've got that data, construct your learning sequence and stay open. The formative stages all the way through it. Every time a new misconception appears or there's a lapse in the misconception, go back and pick it up. This is what formative teachers do. Good constructivist work. And Kate says, do I do one or more misconceptions? And again, I'll refer to Maxine's comment above. The answer is always more. Your learning sequence, if you try to sort of say, I'm going to teach one misconception, then, that's almost strategic negligence. And it flies in the face of what we know about brain science, because we get misconceptions because we've got a series of related misunderstandings. Unless we tackle all the related misunderstandings, then all we're doing is shifting one piece in the misunderstanding puzzle, and we may not be shifting it in the right direction. So it's really important that neuroplasticity, I remember a post this week where I talked about neuroplasticity and the neural strands, and when we have a concept in our mind, it's because all of these strands have wound through our brains and formed around this concept, and here's where the neurons fire. This is our knowledge, this is what we believe. And every time we're faced with this stimuli or this situation, this is our reaction. So in order to unpack those strands, we can't do it just by attacking one misconception. We've actually got to look at that misconception. We've got to break it down. Then we've got to rebuild it, and then we've got to create rehearsal techniques around it so that we can get the students building new neural pathways. So when we're doing that, have a look at your learning sequence. There should be multiple misconceptions evident in that sequence. Or one misconception that is relayed and explored through a whole range of inquiry processes, so that the context of that misconception is completely smashed. If the only tool you have is an inquiry hammer, then hit everything with it. Hit it, like it's a cricket bat. Any questions or comments about those posts? They're there on the forum for you. And this is the good thing about the forum. It's text, so it's obviously real. You can go back there and visit it at any time. But any other questions?
Colin, I have a question. You've answered me this with your email, but I just want to reassure myself for my peace of mind. Mine's actually not a misconception. It's poorly understood. They don't actually understand material, so I actually have to go right to the beginning of the of the stages. So I have to go and actually right to the beginning. That's okay, isn't it? Because it's poorly understood. Is that fine?
Yeah, that's fine. Yeah. That's great, Maxine. Perfect.
Okay, so because I was going to go back to the beginning of the 5E. Okay, thank you. I just wanted to reassure myself. Thank you, Colin. Good.
Feel reassured. That's exactly what you're meant to do. And again, picking up a particular thing. You say, look, what's inside this acorn? They say, tell me what's inside it. But they know you've got the answer, so they're actually they're demotivated. B, but if they sit down and talk to each other about what's inside the acorn, and then they talk to the group about what's inside the acorn, and you list all the ideas, and you form some hypotheses, and then you conduct an experiment with a hammer and smash these acorns and find out what's inside, and we discover it's actually a seed. Okay, so what happens? What grows from seeds? Okay, then we can do another little. These are the sorts of things you do, Max, and you go right back to the start. We don't teach it as a fact.
Yeah, no, I just wanted to reassure myself, because I just thought when you were in the lesson, I'm like, I don't have a misconception, but they clearly did not know, and I clearly need to go to the beginning, but I just wanted to reassure myself, so thank you.
No, that's great. And isn't it sad that they don't even know enough to have a misconception?
Yeah, that's what I was quite sad about, because I went and had a look at the curriculum, and actually in foundation, they're supposed to know that. So I was actually really expecting them to know it, and I was like going, they're going to know this, and I was like really surprised that they didn't know it. So I was like, oh, okay. But so I was quite surprised, actually.
Yes, it is surprising. But then again, it's not surprising too at some levels. Sciences, particularly as we mentioned last week and this week, chemical and physical sciences are not well taught because they're not well enjoyed by teachers themselves. And this is what we've got to do. We've got to get back to levels where we're enjoying what we're doing, where we understand that chemical science is about a whole lot of day-to-day things. Physical science is about a whole lot of average things, like touching my car door and getting a static shock, or rubbing balloons through my hair and lifting my hair. All of these different things are the sciences. And we've got to get back to trying enjoying them and teaching them a little bit better than we do.
Thank you, Colin.
You're welcome, Maxine. Any other questions or comments from people?
Yeah, Colin, I've just got a quick question about the word count. Can we put the learning sequence in an appendix, or would you like to see that as part of the assessment body and the word count?
Look, you have some flexibility there. This is what we call editorial license. You've got 2,500 words. and again, the question for you now is to make editorial decisions about what is important data to include in the body of the paper and what data considers supporting evidence outside the body. Then in part B, how am I going to answer part B? Provide a learning sequence. So what goes into the body? What's the really important stuff that needs to be in the body of that essay? And then what can I hive off to the appendices where a marker who's having a bad day may not even go, because they're not required if it's an appendix. They're only required to read what's in the body. I'd say it's largely unprofessional not to go to an appendices if a student's created one, but some markers don't. I'm not sure that applies to any of ours, but the reality is, if you put something in the appendices, you're making an editorial judgment about it, that it's peripheral to your argument, okay, but it's not your argument itself. So here's the decision you've got to make. What goes in and what goes out?
Okay, thanks, Colin.
Yeah, and it's a tough decision, but once you do it, you'll look and you'll see, no, wait a minute, that's a little bit weak. I've got to work on that. And often you've got little editorial, what we call intertextual devices, where you can say refer to Appendix 1, okay, or a little note, subscript, asterisk, Appendix 2, discusses such and such, okay. For elaboration, go there, okay, and the marker usually will. But then, and they'll applaud your decision. That you've actually had the decorum and the editorial skill to sort of say, well, wait a minute, this is a point which I'm going to need to explain, so I'm going to put that in the appendix. But the key is that I'm including it in my argument. So it's going in the body with a reference to my appendix for further detail. And the marker will actually applaud that, because you're making quite discretionary decisions there, higher level decisions. Any other questions or comments? Ooh, there's 13 of you there, so there's a couple of people being a little bit quiet today. That's fine. Not everybody's up to the same point in time. Learning is not a sequence. It's not like a bus ride. We don't all get on at the same stop, and nor do we get off at the same stop. So it's quite okay. But what I'll do is record this and post it online, and just to invite as many questions as it creates. Encourage you to talk to each other. Encourage you to do your concept mapping. Because what we've got to develop is not a huge body of knowledge about science. We've got to develop a repertoire of practice that enables us as teachers to acquire that knowledge when we need it, to predict when we may have a gap, to predict what that gap may be, given that we know our curriculum, and then to resource ourselves to be prepared to address that. So on that note, if there are no further questions, I will hit the record button and get this up online for people. All right, thank you and good night.
Thank you, Colin. Bye.
Bye-bye.